Good morning and welcome to the session on cryptography, Introduction to Code-Based Cryptography. Today it's my pleasure to introduce to you Professor Paulo Barreto. Professor Paulo Barreto is a cryptographer. He was born in Bahia, a city that's a state that's known for the artists that they produce, but they also produce cryptographers. And he graduated in physics and did his graduate work leading to his PhD in engineering at the University of São Paulo. He's been a faculty member at the University of São Paulo for 10 years. But he also worked in industry for about 15 years, mainly in software development for security and information issues. And his research interest in cryptography is very broad, includes block ciphers, hash function design and analysis, elliptic curve and theorem-based crypto systems, and post-quantum crypto systems, particularly those that are based in codes and lattices, like the topic of the presentation today. He's very well known internationally. I should add that recently coming back from a trip, and I sat next to a guy that was a cryptographer, and I asked him, if he was familiar with some folks in Brazil that were saying, "Oh, Paulo Barreto," and I said, "Yes, I know Paulo Barreto. He's my colleague." He said, "Oh, he was very excited that I knew Paulo Barreto." So, famous guy, and with you, Paulo Barreto.
Good morning, and without further ado, let's begin. First part of our short course, crash course in code-based cryptography. These are our objectives for the whole course. First, just one thing for the organizers. Did you by any means swept my PowerPoint by the PDF back? Because I think this is a PDF. We'll lose the animations if we use. Is it possible to switch back?
Let's see. I think that's
Sorry.
there is a half hour minutes.
Okay. Sorry.
We had some problems in the presentation.
No, but I checked my PowerPoint beforehand. It's there. It's here. It's right here. I checked and everything works fine, so no problems. Okay, so let's go. So, what happens here? Okay. It's just, yes, modern technology. So the first part of our course will be very brief in introducing the basics of coding theory. I know the audience is made exclusively of experts on this subject, so we'll be mainly interested in introducing notation here, and then we will go right into the core subject, which is a panorama of code-based crypto systems. The second part will include security considerations regarding the choice of codes. Not all codes are suitable for code-based cryptography. We'll see a few implementation issues, in particular for the Internet of Things, so it's a modern challenge. Hello? And we will end the second part by having a quick look on modern research topics involving code-based cryptography. So for today, we will focus on the first part. We'll introduce notation, and then we'll have a look at a series of crypto systems whose security stems from hard problems on codes. Okay, so remember, this is just to introduce notation. I will be very quick to introduce this. We'll focus our presentation here on the crypto systems themselves, but just to be sure we are talking the same language, the same mathematical language here. We will only use for our purposes here linear error correction codes. So we'll talk about NK linear error correcting codes. An NK code is a k-dimensional vector subspace of f sub q to the n, the set well, f sub q is the finite field with q elements. So we take n copies, we have a vector of dimension n, a k-dimensional subvector space of that space is what we understand when we talk about a code. Suppose that M is where is it? Oh, here. So suppose that M is composite, P is a prime, Q is a composite power of P, and D is any factor of M. So let S be defined as P to the D. And so we have a sequence of properly contained finite fields. Sorry, oh, here. F sub P is a subfield, finite subfield of F sub S, which is a subfield of F sub Q. So we say that an F sub S subfield, subcode of a code C is the set of all vectors of our code C whose components are completely contained in the finite field F sub S. This will be important more for tomorrow when we discuss Kappa codes, which are subfield subcodes of certain alternate codes. And as I said, the choice of codes is critical for the security of a crypto system. So let's remember this mainly for tomorrow. Well, this is actually trivial. I prepared this for a completely general audience, but the notion of distance we are mostly concerned about when we talk about code-based cryptography is the Hamming notion. So if I don't say anything else when I mention the weight or the distance between vectors, I will refer to the Hamming distance, although there are some very recent works on code-based cryptography that use different notions of distance. But for our purposes, this is an introduction to code-based cryptography. The notion we will use is the Hamming notion. So just to make a link between code-based cryptography and lattice-based cryptography, this is actually the main difference between the two areas. When we deal with lattices, the most popular, the most common notion of distance is the Euclidean distance, and here we will mostly use the Hamming notion. This can completely affect the security of the same abstract cryptographic construction. If we change the notion of distance, we can have a very strong crypto system or a completely broken one. Okay. Well, there are obviously two simple and equivalent possibilities to define a code, to specify a code. Since it is a vector subspace, we can specify it by providing a basis. So we simply list them as the rows of a particular matrix, which is the generator matrix G. So the code will be the set of all linear combinations of the rows of the generator matrix G. Or the second possibility for defining the same code is to actually give a basis for the orthogonal code, the dual code, the dual vector space. Since it's orthogonal, the projection of code words onto that subspace will be 0. And so we can also define the same code as the set of vectors of the whole vector space whose projection on the dual code is 0. If it is not 0, we probably are dealing with a code word with errors. If there are not too many errors, we can usually correct them. A syndrome is how we call the projection of a certain vector onto the dual code. But you know that. I'm only recapping the subject. So there are two very interesting computational problems regarding codes. Classical problems, which are the general and the syndrome decoding problems. There are actually two ways of defining the same hard problem we have to solve according to how we specify the underlying code. I think it's swept here, but no problem. If we specify a code by its parity check, by one of its parity check matrices H, we are given this parity check matrix plus the dimensions, the code length N, the code dimension R, the dimension of the dual code, and a certain bound on the number of errors we can correct. And finally, we are given a certain syndrome, a projection of some vector onto the code whose generator is 8. So it's the dual code of the code we are actually interested in. We have to answer this question: is there by any chance a short vector, a vector whose Hamming weight is limited, its upper bound by t, whose syndrome is S, is the given syndrome? Of course, it's easy to obtain a generic solution to this linear equation. The point here, the hard part here, is to ensure that the solution is short. So most of the elements are 0. Is there any such vector? There may be one or not. And answering this question is as hard. There is a completely equivalent characterization of this problem when we are given a generator matrix for the code instead of a parity check matrix. But it's actually the same thing. We are given the generator matrix G, the code length N, the dimension K, and a bound T for the number of errors. And here we are given a certain vector C, the containing vector space. The question we have to answer is there any linear combination of G? So is there any code word, any proper code word whose distance to the given vector C, this is the difference, so it's essentially the distance, whose distance is upper bound by T? The two problems are equivalent because we can simply map one of them to the other and vice versa. So how do we solve or try to solve this problem? We usually map this vector to its syndrome and try to decode it. We actually map the general decoding problem to the syndrome decoding problem. So we can do the opposite. as well. So these two problems are equally hard, and they are both NP-complete. So the corresponding search problems are NP-hard. So this is what inspired the creation of the very first code-based crypto systems. As soon as the syndrome decoding problem and the general decoding problem were proven to be NP-complete, it was a matter of months before the very first code-based crypto system, the McEliece crypto system, was proposed. It's almost as old as public key cryptography itself. Public key cryptography was discovered publicly, at any rate, in 1976. The popular RSA crypto system was devised in 1977, and McEliece was published in 1978. So less than 2 years between the invention of public key cryptography and the creation of the first code-based crypto system, the McEliece crypto system. If I am not mistaken, the proof that the syndrome decoding problem is NP-complete was published in 1976 or 77, so it's almost the same time. Okay? Well, and this is the inspiration for code-based cryptography. It's not exactly the same as those two hard problems. Code-based cryptography is inspired by the hardness of those and other problems as well, but it's not equivalent to those problems. Okay, we know there are codes that admit an efficient decoder. In general, if we are given a completely random code, we don't know how to efficiently decode up to a certain limit, but there are codes that we can construct so that they do admit an efficient decoder. Crypto systems can be built upon those codes if two conditions are met. The first one is that the efficient decoding trapdoor, the efficient decoder, can be securely hidden. If the trapdoor is not hidden, then it's not a private decoder anymore. It becomes public. So the trapdoor has to be hidden in some secure way, so that only an authorized user can use it. It's also necessary that one, either these two problems or a related problem remains hard, not only in the worst case, because this is what NP-completeness actually means, there is a hard instance, but for cryptography, what we really need is that most instances are hard, so it's hard on average. We don't have any proof that code-based cryptography is hard on average. What we do know is that for decades people have tried to find an efficient way to decode generic codes, and we don't have such a decoder. And when we consider how we can actually tackle these problems or others, the fact that we know the problem is hard in the worst case usually is not relevant for the method we have. So it all happens as if most instances were equally hard to tackle. It's certainly possible to come up with a few easy instances, but if we pick a suitable code, if we choose the code properly, then what happens is that a randomly generated key will be as secure as the hardest key possible. This is merely an empirical observation, not only from the implementation point of view, but also from the research point of view. We don't have any theory that makes use of the fact that all we know for sure is that there exist hard instances. In practice, most of them are equally difficult. So this is exactly what we need to define crypto systems based on codes. For a matter of practicality, we will only deal with binary codes from now on. This does not mean that we cannot define crypto systems on top of non-binary codes. I mean, we can go to odd characteristic or keep using codes in characteristic 2, but resorting to higher extensions. But in practice, what we really use is binary codes. So they are defined in the end over f sub 2. They are also the easiest to implement. There is not really any evidence that we can get better codes when we go to higher characteristics. So let's stick to the binary case. It will simplify things a lot. Okay, so this is all I had to say about the basics. As I said, it was mostly a matter of introducing notation and talking a bit about how cryptography got to be inspired on coding theory. Let's go now to the focus of this first part, which is having a look on several interesting crypto systems whose security is based on coding theory. Okay, so let's begin with chronology. As I said, the McEliece crypto system, which can do only one thing. It was devised to encrypt information. It's not suitable for digital signatures or anything else. It was invented in 1978. In 1986, a second encryption scheme was devised. The difference between McEliece and this second scheme devised by Harald Niederreiter is that McEliece uses the representation of a code that uses a generator matrix. Well, we can represent the same code using a parity check matrix. This is exactly what the Niederreiter encryption scheme is all about. Instead of using a generator, we use a parity check matrix here. It does not mean that the two schemes are completely equivalent in practice. The security level is exactly the same. We can actually reuse the essential part of a public key from one crypto system to implement the other one, and vice versa. But Niederreiter tends to be a bit more efficient. So if we have to choose between one or the other, my recommendation is to use Niederreiter. A syndrome is always shorter than a code word with errors. So at the very least, we are saving some bandwidth, but there are other possibilities for enhancing performance or so. Okay, so in 1993, different scheme was devised. So here we only have encryption. How about identification? I want to be sure that a certain user is really what or who he or she claims to be. Possibly through an insecure channel using public means. I want to be sure that a certain user is authorized to access a system, a computational resource, or whatever. It's possible to do it with a scheme devised by Jacques Stern. There is a recent alternative to that one. We'll see both of them here. In 2001, okay, we can also modify Stern's identification scheme to obtain digital signatures, but they are not very efficient. We will see why. In terms of signature size, they are very, very large. In 2001, the first scheme that had, at that time, had the chance of being efficient, because the signatures are very short, was devised. CFS are the initials of the designers, Courtois, Finiaz, and Sandrier. We'll also see that although signatures are very short, keys are enormous, and signature generation times are equally long. So they are neither the signature scheme based on Stern's identification scheme nor CFS signatures are really practical. But it's possible to obtain code-based signatures, although they are not really practical. In 2009, Jean-Philippe Querelle and co-authors devised an arcane, very interesting, it's a crypto system whose properties are really different from what we are used to think about when we hear cryptography. So encryption, perhaps signatures. So here we have identity-based identification. When we talk about public key cryptography, what is behind that is that each entity has his or her own private key and also a public key, so everybody can publish their keys and exchange messages. But we have to compute the public key from the private key. We cannot choose what the public key will look like. When we talk about identity-based cryptography in general, it's exactly the opposite. We choose what the public key is. It could be, for instance, an email. That is a user's public key. Okay, so how about the private key? We have to compute the private key from the public key. And here we begin to see that it's not really obvious how to do it, because if one user can do this, can pick a random string like an email address and extract from it a private key, why can't any other user do exactly the same? I will not tell you how to do this right now. It's possible. We don't know how to do full-fledged identity-based cryptography using codes. Here is what we have is identity-based identification. We can do that for an identification scheme. It's terribly inefficient, but we can do it. So it's a kind of hint that maybe we can do more. This is one of the research opportunities I will talk about tomorrow. Sorry. And there are other schemes, completely non-intuitive. We can do some very strange things, actually, using code and cryptography in general. But we will have only time to have a look at the basic schemes here. So let's begin with the most classical one, the McEliece crypto system. So we have to generate a key pair, a private key and a public key. How do we do that? So we have to choose a secure code. We'll see tomorrow how to do it. It's possible to do it. So uniformly random T error correcting NK code C over F sub 2. The binary code equipped obviously with some efficient decoding trapdoor. This will be part of the private key. This will be part of the secret. Usually the decoding trapdoor is one very, very, very special basis of the dual code. So it will be a unique or near unique parity check matrix, which here we represent by H hat. So it's a binary R times N matrix. The unique form of that matrix depends on the nature of the code we choose. And then we compute a systematic generator matrix G for the same code. That's quite easy to do. It's only a matter of solving a linear system to obtain a systematic basis for the code. And the private key is H hat. The public key is the generator matrix G and the number of errors we can introduce. And that's about it. This is the basis of the McEliece crypto system. Now, it's possible that some of, or most of you have already had a look at how McEliece is by reading a textbook or so. So it's not unusual when we present this that someone in the audience tells me, no, I know McEliece. This is not what my textbook tells me McEliece is. This description is wrong. It's not wrong. It's a more modern view of McEliece. Those of you who have already had a look at McEliece probably saw something like this. The private key would be a generator matrix G hat. The public key will be computed from it by choosing a uniformly random invertible matrix. S comes from scramble. It's called scramble matrix. And a uniformly random permutation matrix P. This description is actually equivalent from a security point of view to the one I just used it here. Because the actual form of the scramble matrix S is relevant for security, particularly for semantic security. We'll see when we see how encryption works, why this has to be so. The matrix S is not directly related to the security of McEliece. And to be sure, the permutation P actually introduces an implementation vulnerability in the system. There is a paper published in 2009 or 2010 that shows that applying the inverse permutation to decrypt a McEliece cryptogram usually leaks information about the trapdoor. In practice, it's not a problem in the algorithm, it's how the algorithm is implemented. So it's a bad idea to use an explicit permutation P. But if we keep the permutation secret, if we apply it when we are generating the key pair, and we keep it secret, we keep the code already permuted, and instead of choosing a completely random scramble matrix S, we use the matrix that takes this one and puts it into a systematic form, we get not only an equivalent public basis for the same code, but also a more efficient one. If it's in systematic form, we have a big chunk of the generator matrix, which is simply the identity matrix. So we don't have to store it or to transmit it or even to process it when we are multiplying by the generator matrix. We don't have to multiply by the identity matrix. So it's a good idea to use the presentation of McEliece. I just use it here. It's more modern, it's more secure, it's simpler as well. Sorry. Okay, so how do we encrypt? We are given a generator matrix. Assume we have a message M whose length is k bits, so it can be used to define a code word. It defines a linear combination of the rows of G. This is exactly what we do here. But then we choose a random error pattern E, whose weight is T. T is a parameter of the system. It's chosen so that correcting the T errors is hard, and we introduce those errors. So the code word with errors, C, is the cryptogram, is the cipher text associated to message M in the McEliece crypto system. If you think about it, this scheme leaks information trivially. If M is a real message, if it's a text message, for instance, and G is a systematic matrix, then M times G will be the same message together with a kind of checksum, but we can still read the whole message. And there is something random looking at the end. Then we introduce a few errors. We flip some bits. We can still read most of the message, with exception of a few typos. Whenever we flip a bit, we introduce some small error in the message. But if it has enough redundancies, we can still derive what the whole message is. So it leaks information. M cannot be a low entropy message. It has to be essentially random. We'll see in the next slide how we actually do that. But anyway, before we go there, how do we decode? Well, that's really easy. We are given a code word with errors. We compute its private syndrome. We use the private parity check matrix H hat. So S is a decodable syndrome because it corresponds to the error pattern whose Hamming weight is only T. We chose the code so that we can correct T errors. So we recover the error pattern E. We remove the errors from the code word. And because we forced G to be a systematic generator matrix, we can simply read M from the first K components of C minus K. And that's it. It's very simple. It can be very efficiently implemented, particularly if matrix G has some kind of external symmetry, like it's a quasi-cyclic matrix or so. So multiplying a factor by a matrix with this symmetry can be done very efficiently. Usually the decoder is also very efficient here, so in terms of performance it can be competitive with other options, non-code-based crypto systems. But it leaks information, so we have to seal the leak. How do you do that? There are several ways. I will show one that is not the most efficient one, but it's one of the simplest. It's called the Fujisaki-Okamoto transform applied to McEliece. There's one setup. We have to choose a few cryptographic primitives about which I will not talk. I will define what they do, but not how to obtain those primitives. we need two primitives here, two random oracles. What is that? It's not a horoscope, nothing of the kind. Random oracle is essentially an ideal hash function. Here we are using two. What we need is a secure message of authentication code and a secure symmetric cipher. So it's plain cryptography. It's not usually based on coding theory, although designing those primitives can involve some coding theory as well. But here, what we have is a function that takes one linear combination that gives a code word plus a message, a random sequence of bits, and produces an integer mod n choose t. This is the number of error patterns of length n and Hamming weight t. It's a combination of n, t by t. And E is a symmetric cipher, actually as a simple string cipher. We feed a key, a symmetric key, which we take here to be a sequence of k bits. So we can use the same parameter here and here, and it produces a random looking sequence of bits. It's essentially indistinguishable from a sequence of truly random bits. We usually abstract everything and assume that it's completely random. We have to use a permutation ranking or unranking function. I have an appendix to these slides. I will not talk about them, but anyone interested can have a look at the appendix afterwards. It's a way of taking an integer mod n choose t. So this is the number of possible error patterns of length n and weight t, and this function gives the corresponding error pattern. It's a vector of length n and weight t. There are several ways to do this, and apply the inverse transform as well. So let's just assume we can do this. And we, of course, we have to have the efficient decoder. It's an algorithm D that takes a syndrome and produces an error vector, an error pattern. It has to satisfy this requirement. When given the privately decodable syndrome of any error pattern of Hamming weight t, it will yield exactly that same vector. What happens when we feed the decoder with anything that does not satisfy this restriction is not specified. It can fail. It could even succeed under some circumstances. Sorry. But all we really need to ensure is that when we provide it with the syndrome of a short vector, it can compute that short vector. So how does encryption work here? We cannot simply pick the message and multiply it by G and introduce errors as we saw, but we can generate a completely random code word, so there is no semantics embedded in it. So Z is a representation of a linear combination. It's a vector of length k. We will multiply it by the generator matrix here. So Z times G is a code word. We will introduce a very special error pattern here. We will compute a message authentication code for message M using Z as its key. So it's a hash with a key. The result is H, is an integer mod n choose t. So we can now use the unranking function U to take that integer and obtain the corresponding error pattern E. We add the error pattern to the code word. So W is a blurry code word. It will be part of the complete cryptogram here. How do we encode the message properly now? So M is our true message. we feed the same Z to string cipher, a symmetric encryption function. It will produce a mask that is indistinguishable from a sequence of completely random bits. It will emulate a one-time pad, and we mask the message bit by bit using that. So D will be also indistinguishable from a sequence of random bits. This is the complete cryptogram. I'm not proof that this is secure. There's a proof in the Fujisaki-Okamoto original paper. It was published in 1998 or 99. How do we decrypt is exactly inverting what we already know about McEliece and also the symmetric part. So, given a ciphertext which is a pair W and D, first we compute the private syndrome of W, we get S, we apply the decoder to S, and since it corresponds by definition to a short vector E, the decoder yields that error pattern E, so we can now remove the errors and extract the very first, this notation means take the first K bit, so we read the first K components because the generator is in systematic form, and this way we recover Z. So now we can feed Z to the symmetric cipher. It generates, it computes the same sequence of bits. We apply an exclusive OR again, and we remove the mask. We get the message M again. How do we know that decryption worked correctly as expected? We have to check if we obtained the right message. So using Z and the message M, we can recompute the message authentication code H and produce an error pattern V. We only check that V equals to E. If it does, then everything went well. Everything, question?
Yeah, so basically what we do here, we use one-time pad and we encrypt the key with McEliece.
Yes, it's an emulation of a one-time pad. It's not really a one-time pad because it's deterministic. It does not involve real randomness here, but we emulate it. We protect the message in computational terms. The one-time pad is unconditionally secure, and McEliece, even with Fujisaki-Okamoto, is only computationally secure. Because if anyone can solve the decoding problem, then they can break the system. It would be impossible if it were a true one-time pad. It's only because of that. We are inspiring our scheme in a one-time pad, but it's not quite a one-time pad. It's the same idea, the same intuition. Okay? So, and that's it. This is a secure instantiation of McEliece in all aspects, using the Fujisaki-Okamoto transform. There are more efficient ways to do it, but they are much more complicated than this. So let's stick to this. So how about the Niederreiter crypto system?
Sorry, one question. What's the property of H hat that makes the decoding easier? Because I assume
we'll see that tomorrow. Here we only assume we are making. It's a very strong assumption. We are assuming that we can build an error correcting code that admits an efficient decoder, and we also can hide that decoder somehow. The principle of hiding here is a needle in a haystack. So there is one very particular basis for the code, or its dual, using which we can decode. Any other base will be bad, or almost any other basis will be bad for that. So we publish one of the bad bases, and we privately use that very particular, almost unique basis for decoding. What the private basis looks like depends on the code. There are not that many choices. Because you see, the problem is actually intractable, it's hard. But we do know some codes that admit an efficient decoder and also admit a secure way of hiding the trapdoor. Tomorrow we'll be addressing this problem here. So let's just assume it's possible tomorrow. It's the natural question. So, how do we actually do that? Can we implement it? Yes, we can. Tomorrow we'll see that. Don't miss tomorrow's second part. Some advertisement for tomorrow. So let me just check how much time do we have here. Okay. So Niederreiter will use the dual representation. Instead of using a generator matrix, we will use a parity check matrix. We need a semantically secure symmetric cipher as well, but here the key will be an arrow pattern. It should be clear here. The key to the symmetric cipher will be a vector of length n and weight t. The other parameter will be our message, a sequence of bits. It will produce a cryptogram or perhaps an indication that the operation failed for any reason. For encryption, it's hard that anything will go wrong here, but for decryption, it's possible that we get an error indication. We feed the inverse of this encryption function something that is not a cryptogram. It will tell us, no, this is garbage. This is not true ciphertext. Okay, so given this, we choose a code, etc. Exactly the same thing, but here, instead of publishing a systematic generator matrix for G, we will publish a systematic parity check matrix H for the symbol. So there exists a matrix M hat. It's a unitary matrix. It has to have a determinant 1 because it's only a change of basis matrix here that maps between the public matrix and the private matrix. I could have put the M here. I chose to put the M there because notation gets a bit simpler. Okay, so there exists a non-singular matrix M hat that, when we multiply it by H, yields back the private parity check matrix H hat. So the private keys is this pair of matrices. The public key will be H, and also the number of errors we can introduce. Since H is in systematic form, the essential part of that matrix can be exactly the same as the essential part of a generator matrix for a McEliece public key at the same security level. That's why I said they are equivalent. They can share a public key. The McEliece public key will be a systematic generator, and the Niederreiter public key will be the systematic parity check matrix for the same code. Okay? Yes?
Sorry, why do you have both M hat and H hat in the private key?
Because we will have to transform a non-decodable syndrome into a decodable one. We'll see in the next slide that a cryptogram is a syndrome, but not a decodable one. To be able to decode it, we have to modify it. You see?
When we have M hat and H, so you don't need H hat as a part of it.
You mean here?
Yes.
No, you must have it.
But you have H,
H
right?
computer.
This is the public key.
Yeah, I know, but
This-
the user has the problem.
Oh, you mean when the user needs M hat, he can compute it. Okay, I put it here because it's more efficient. You only invert the matrix once. Actually, you compute M when you are creating a key pair. It involves solving a linear system. It's kind of heavy, so let's do it. I mean, it's much more efficient if you do this only once and you keep this. Well, since it's secret, you have to protect H hat, protect M hat to keep both ready for use. But it's possible. You can certainly keep only one of them because the other is public, and given one, we can compute the other when needed. Sorry, oh, okay, yes.
Is it without loss of generality?
Sorry,
Is it without loss of generality you restrict yourself to error patterns of exact equity rather than a certain
more or less. I mean, if by any chance you get an error pattern whose weight is much lower than t, then the system can become insecure. So in practice, what you do is introduce exactly t errors. You don't need shorter errors. Actually, the number of available vectors, the number of available extra vectors will not be much larger. You get a few 3-4 bits in practice. So you don't change your security level in any substantial way. Implementation gets simpler if you do exactly that. So, and you also avoid the possibility. It's rare, but there would be a possibility that the number of errors gets so small that decoding that many errors gets easy. So you have an assurance that decoding t errors is hard. Decoding less than t errors can still be hard. T minus 1, t minus 2 should be okay, but half as many errors would not be okay in general. Okay. How do we encrypt? Well, it should be obvious by now. We generate a random error pattern. We compute its syndrome using the public parity check matrix, which is part of the public key, so anybody can do this. We use the error pattern E as the key to encrypt N, so we have the message proper encrypted in D, and the complete cryptogram will be S, the syndrome, and D. Okay? How do we decrypt? Well, see here. S is not a decodable syndrome. It's a syndrome associated to a matrix H. That is, if everything was done correctly, indistinguishable from random. It's as if we had a uniformly random error correcting code and we are given a syndrome. The problem is hard. We know it's hard. So that's not good. But fortunately, we know the trapdoor. I mean, the legitimate user does. So first thing is to transform the given syndrome into a decodable one. We change the basis from a bad one. It's the needle in the haystack principle. Instead of working with a haystack, we use the needle. We know exactly where the needle is. So we map from bad basis to the good one by here multiplying by the transpose of M hat. So now S hat is actually a decodable syndrome. So it's only a matter of seeing how the math works out here. S hat is the H hat syndrome of the error pattern E. So we can decode it using the trapdoor, and this is exactly what we do. We decode the syndrome S hat and we get E. And then we decode the rest of the message. The inverse algorithm returns either the original message M or an indication of failure when it's not a cryptograph, so we know if decryption was successful or not here. Okay? It's as simple as that. and completely equivalent from the point of view of security to McEliece. But it should be clear from here that it should be more efficient, at least, at the very least, in terms of bandwidth occupation, because here we have a syndrome. In the other case, we had a blurry code word, has to be longer code word than the syndrome. The code dimension is smaller than the containing vector space dimension n. And that's it. Okay, so,
Well,
yes.
In the original McEliece scheme, Fujisaki was unavailable. Right?
No,
So how did he do
he didn't.
it? Didn't.
No.
So
I mean,
that's
he tried to argue that the scramble matrix could make do, but it can't. Some papers were published right afterwards showing that it's not the case. I mean, if you do use a random S, then you will hide a message, a text message, for instance. But there are ways to overcome that and recover information, sufficient information about the message to read it, except for perhaps a few parts again. So it's not, in particular, if you emulate a network failure. I didn't receive your message. Could you please encrypt it again? The same message, encrypted differently. You can take the difference. You don't have the decoding trapdoor, but you analyze the difference. You can recover the message. So it's not secure. You really have to use some security transform like Fujisaki-Okamoto to make McEliece secure. There were some ad hoc ways to use it, but no security proof. Fujisaki-Okamoto was perhaps the very first one for which you have a security proof. If anyone can violate the security assumptions, then he or she can also solve the underlying hard problem, which is in that case distinguishing the public generator matrix from a completely random one. So this is the actual hard problem underlying this construction. It's not exactly the syndrome decoding problem. You're not required to show that you can decode. All that is required is that you can pinpoint if you have a completely random code or one whose nature admits that particular trapdoor or another one. Okay, so for instance, it's possible to distinguish a copper code. We'll see this tomorrow. It's possible to distinguish a copper code from a random code. There is a very recent algorithm, I think it's 2011 or so. The correct date is on a slide, if I'm not mistaken. Using a completely public algorithm and the public key, you can tell if that generator matrix corresponds to a copper code or not. So the assumption that a copper code is indistinguishable from random does not hold. This was discovered 4 years ago. So research always progresses, but you can use other codes and also other security transforms. You don't need to use Fujisaki-Okamoto. There are other transforms that do not require the code to be indistinguishable from random. So not always is lost here. Okay? So let's go. So that's enough for encryption. Let's see digital signatures. Very hard to achieve with codes. CFS signatures. The overall setup is essentially a hash function, but a hash function here that accepts not only the message as a parameter, but also a counter. You need a counter, natural number, 0, 1, 2, etc. And produces a random-looking syndrome because the length is r, is the code dimension. Oh, how do we choose? How do we build a key here? It's essentially the same way that we build a Niederreiter key. So this key was based on Niederreiter. If you compare this paragraph with the corresponding one, Niederreiter, you see that the difference is only this part in italics. So we have to choose a code with a high density of decodable syndromes. Now that's hard. But okay, let's assume we can do it. Everything else is the same as Niederreiter. So let's just see how do we sign. So having a high density of decodable syndromes does not mean that we will be lucky enough that in the very first attempt we will get a decodable one. We may have to try several times. So we map our message M and a certain counter I to a syndrome. And we transform it to a decodable one. So this is a public syndrome. We map it to a decodable one by multiplying by the transpose of M hat. Since C hat is decodable, we decode it, or we try to decode it. I mean, we are assuming that it is. It may or may not be decodable. Okay, try to decode it. What if it is not decodable? Increment the counter and try again. So find the smallest counter such that when you do this, C hat is a decodable syndrome. Okay? If you do this, well, then you are producing a public proof that you know the trapdoor for this code. You were given a random-looking syndrome that involves the message you were trying to sign, plus a counter, hopefully a small one. And since it's a syndrome of a short vector, you can present that vector as evidence. Here is a short vector whose syndrome corresponds to the hash of that message with this counter. So the whole signature is the pair short vector E and the counter value. How do we verify that? Well, compute the public syndrome C and check if the hash of the received message and the counter, the second part of the signature, match. Okay, and that's it. It looks easy enough. In principle, it is. But remember, we need a code with a high density of decodable syndromes. That's very hard. The best known codes for CFS are GOPA codes. When you compare with the density of decodable syndromes in other families of codes for which we know how to securely hide the trapdoor, the corresponding trapdoor, GOPA codes are the best available. At least to my knowledge, it's possible that by now someone has designed some other family of codes that satisfy all requirements. I'm not aware of anything of the kind, so GOPA codes are still the best. But they have a problem. The density is 1 over t factorial. T, the number of introduced errors, the weight of the produced signatures. So how many steps do we foresee that we'll need until we see a truly decodable syndrome? What is the value of the counter? What is the expected value of the counter I? T factorial. This is much worse than exponential. So, but okay, not all is lost yet. we can play with the parameters. So the authors of CFS suggested using a very small t, of course. T has to be very small because of this. And we compensate to attain a suitable security level by choosing an extremely long code. They didn't quite succeed, but okay. Signatures are very short because of this. The length is essentially the length of one syndrome. We can also see this in another way. We only have to specify the coordinates of the t bits that constitute the error pattern. If we have, say, a code of length 1,000,000, the number of bits you need to represent an integer between 0 and 1,000,000 is 20. So the length will be 20 times t. It's linear in t. T is small, it has to be small. Signatures will be very short. That's okay, but the public key is huge. Together with the fact that it's hard to increase the security level. We have to increase t, and then signing times will be very bad. How bad? The animation here failed, but okay. Let's begin with that table. Anyway, these are the security levels we attain for this combination of the it's a parameter related to finite field f sub 2 to the m. It will be related to the code length. M is the logarithm of the code length. So here the code length is 32,000, more or less, and here it will be about 4 million bits. This is the number of errors. I don't advise you to take anything larger than 12, because 12 factorial is already enormous. It's 2 to the 44 or so. So security levels that you can attain are in green. The original parameters proposed in 2001, the authors thought it would be 2 to the 80, more or less corresponding to RSA 124, but it's actually much lower than that. Hundreds of thousands of times weaker than what they thought. So we have to increase m and t to get at least to the borders, to these borders of this rectangle. What is the drawback here? Well, so first, because the animation failed here, I'm sorry. Why is the security for m equal to 16? So it's 65,000 bits for the code length and 9 errors. Because there is an attack, it was discovered the next year. They published in 2001, 2002. An attack was discovered that reduced the security level. So I have to take larger keys. It's possible there are some tricks to reduce keys by a factor of 2 or 4, but that's about it. How large are keys anyway? So this is the key size in megabytes. For this combination, keep in mind that signing times here are of order 12 factorial. It's enormous. 0.7 megabyte. No, that's too long. I need something very fast. Okay, so t equal to 9 is 400,000 or so. Then m has to be 22. Your code will be 4 million bits long, and the key size will be 99 megabytes. And the security level will be 2 to the 80. No, this is low for nowadays standards. I need something more secure than that. Well, you can go in that direction. Keys here are 132 megabytes long, and processing times are, well, perhaps it would be interesting if you begin the signature process and you go out on vacation when you get back. Perhaps the signature is ready. So it's okay. I mean, it's not impossible to get signatures this way, but nobody in his or her mind will actually adopt this. I'm so sorry, but anyway. So stern identification. Let me only check the time. Oh, 15 minutes. Okay, no problem. Here. So this is only a way to prove your identity. How do you do that? We will prove that we know not a decoding trapdoor. It's not necessary here. We will prove publicly that we know how to decode one particular syndrome. Just one. So how will you decode that syndrome? Well, we won't. We'll do the opposite way. We'll choose a short vector computed syndrome. The syndrome will be our public key, and we will show, without revealing what the error pattern is, we will prove that we know that short error pattern. So for this, we need a uniformly random, completely random, no trapdoor here, parity check matrix H. Usually the code length is twice the dimension or code dimension. It's R by 2R, which is 2 squares. In systematic form, so we have only to store one square matrix. And there's an obvious improvement here is by Gabory and Giraud, which is, well, choose that square to be a circulant matrix, so you only have to store the first row. It's very compact. We'll see some proposed parameters here. So keys are very, very short. Here there is no trapdoor. Codes are completely random, so decoding is really hard, for all we know. Private key is a random error pattern. The public key will be its syndrome. We know only how to decode this syndrome, no other, unless we do the same again and again. Several users can even share the same parity check matrix because it's completely random. It has no trapdoor, but each user will have his or her own key pair. Okay. Stern identification has 3 steps. It's a commitment. We will promise something. We are the people who want to prove that we know the error pattern E. So we'll make some commitment. Then the challenger will provide us with a challenge. Using that commitment and the challenge, we will answer the challenge. There is a probability of cheating, but if we repeat this process several times, the probability that we are cheating drops exponentially. This is the principle. Now it's rather technical. So it would be possible to check the math here, but we won't have time. Anyway, only to have a quick overview here. What is the commitment? We are the prover. We know the secret error pattern. We are the prover. We choose a uniformly random word, not necessarily a code word. It's a random word of length n, and also a uniform permutation on n-bit words. Okay, it's a permutation. It's a way to move around the bits in an n-bit word. We will send 3 hash values to the challenger. We will hash that random word U permuted according to the permutation we choose, sigma. So we hash it. The challenger cannot know what sigma and U are by seeing only its hash, but if he or she gets to know what sigma and U are, then it's easy to check that C sub h is correct. We will also send the permutation sigma applied to our private key masked with U. Now this is a one-time pad. U is completely random. We are masking our error vector with a completely random vector. So essentially we have a random n-bit vector here, and we also permute its bits here. And finally we hash the permutation together with the syndrome of that random word U. What's that? Yes?
I guess it was not explicitly mentioned.
Sorry,
Yeah, I guess it was not explicitly mentioned, but H is part of the private key.
you mean this H here? No, it's a public parameter. You can see it here. So it's part of the setup. It can be shared between users. Since it's uniformly random, it does not contain a trapdoor. You have to ensure it's random. It's really random or random looking. Say it's the hash of the of a string of zeros using a cryptographically strong hash function or so. So everybody knows H. Since it can be shared, it's not necessarily part of the public key, but it's part of public parameters. Okay? Your public key is only a syndrome of a short vector computed according to that public global parameter. Okay? So C sub 0, C sub 1, C sub 2 are the three parts of the commitment we send to the challenger. Then the challenger will choose a trait, not a bit, a trait. It's a value in the set 0, 1, or 2, which means reveal something else about commitment number B, C sub 0, C sub 1, C sub 2. Reveal something else. What else do we need here? I'm sorry. According to the value of B, if B is 0, we will reveal E masked with U. So this is a part of, this is our private key encrypted with a one-time pad. We are not revealing anything about E, but we reveal sigma. If B is 1, we reveal U and sigma. Well, they are random. We are not involving the private key here. And if B is 2, we apply sigma to E and to U. We are revealing this. Are we really revealing anything about the private key? No, because any vector of length n and weight t is a permutation of any other given vector of the same length and the same weight. So it's essentially a random error pattern. We are also revealing the same permutation of a random and unknown vector u. So we are not revealing anything really with this, but we already committed to some values. So we reveal either this, or else this, or else this, but not everything together. And we send that back to the challenger. Then the challenger can verify that two out of three commitments are correct using those pieces of information. So if B is 0, the verifier can check that C sub 1 and C sub 2 are correct. The maths are here. If B is 1, then the verifier can, the challenger actually, can verify that C sub 0 and C sub 2 are correct, because enough information was revealed to allow for these checks to be made. And finally, if B is 2, the verifier, the challenger can check that C sub 0 and C sub 1 are correct. There is a probability of cheating here, of succeeding to provide the correct information by chance. That is 2/3. It's actually a bit high, but if we repeat this process sufficiently large number of times, which is given by this expression, then we can reduce the probability of cheating below any fixed upper bound. Okay, so it's probabilistic. It's possible. I will skip this part. It's very detailed. It's algorithmic here. It shows how to obtain a signature scheme from the identification scheme. It's called the Fiat-Shamir transform. Okay, I will skip this. As you see, it's the complete algorithm. The overall idea is that we will emulate the challenger by using a hash function. We'll make a commitment related to our own inability of inverting a cryptographically secure hash function. The details are here. The signature will be essentially publishing the information we need to check a certain number of challenges that, although they are related to something we know, we don't actually have control upon. So if we don't have control, everything is as if we were receiving an actual challenge. You cannot choose what challenge we will get, because it will be the output of a cryptographically strong hash function. Unfortunately, because we have to include in the signature a considerably high number of challenges, signatures will get very large. Keys are short, but signatures are large, and processing times are large. The main are large as well. Sorry. We have a loop of length n here. If n is 100, we have to repeat the same computations 100 times. So it's kind of slow. To verify, same thing. So we have here an expression for the actual signature size. I think I have. Okay, it's in another slide here. If we introduce parameters here, as I'll show you. 2 minutes. In 30 seconds, I will show you how the parameters look like, what the parameters look like. But signatures are actually very large here, so they are not practical. There is a better way to do it. It's called the AGS identification scheme by Aguilar, Gabory, and Shrek. This Shrek here is not the one by Pixar. It's not married to Princess Fiona. It's not the same one. But what is the advantage over a Stern? Let's skip this. Right, so here, lots of technical things. Here, okay. The probability of cheating is only 1/2. So it's more efficient, because we don't need as many steps, as many commitments, challenges, and responses as in the original Stern scheme. But it's not that much more efficient. Signatures are shorter. Signing and verification times are smaller as well, but not exactly practical. They are not competitive with any other signature scheme using different computational assumptions. Okay. Okay. Here the keys. So key sizes are private keys are 2 bits. 2 times r bits long. Public keys are r bits long. They originally proposed r equal to 347 bits. It would be better to increase a bit, but not by much. So a few hundred bits. That's quite short. Signatures are enormous. 122 kilobytes for legacy level setting. Oh, and the generation times are long, but not as long as in the case of CFS signatures. Those signatures are still a research problem when we are dealing with code-based cryptography. I promise you to give a feeling of what those more arcane crypto systems look like. Identity-based identification, the only construction we know, use GOPA codes and the Stern scheme. So that H, that parity check matrix H in Stern's identification scheme originally is completely random. What if we had a trapdoor there? What if a trust authority, a key generation center, does know a trapdoor because the code is not a random one, but a GOPA code? Then we can compute private keys from public keys. So a public key in this scheme will be the user's identity. The private key we will give that user will be that identity mapped to a decodable syndrome. The trust authority can decode that syndrome. And we use the result as a private key for CFS signatures. We have to modify the CFS scheme a bit. Instead of decoding to T errors, we have to decode to a vector with slightly increased weight, T plus delta, so that T plus delta is at least the cover radius of the underlying code. And the result is a new functionality, a new cryptographic functionality. However, since it involves CFS signatures, as we saw, keys get really hard, 100 megabytes or so, and the times are very, very long, T factorial, not T plus delta factorial, only T factorial. We cannot avoid that part. So it's more of a proof of concept than a practical application. It's also possible to do code-based hashing. We use the hash functions a lot here. They have to satisfy at least two conditions. They have to be pre-image resistant, so given a hash value you cannot get back, and collision resistant, given a hash value you cannot find two messages that hash to the same value. It's possible to design hash functions that are collision resistant, and you can prove that they are, because finding a collision is as hard as solving a syndrome decoding problem. They give those names fast syndrome-based hash and really fast syndrome-based hash. They are slow, painfully slow, so it's another case of a proof of concept. It's possible, but not really practical. Okay, so that's it for today. Any more questions you have? Minus 5 minutes or so. Take your questions. Yes.
Any practical applications do this code encryption used to practice?
Yes. Actually, there are several people from industry that are paying research. I got a project from Cisco. They were interested in using code-based encryption. It would have to be very efficient for use in their routers, and also lightweight enough to be adaptable to mobile devices or the Internet of Things. We show that it's really possible. Their focus was exclusively encryption, so we didn't face these drawbacks of signatures. I will present some results tomorrow about implementation. You can implement code-based encryption on very constrained devices actually, and the results are very competitive. I mean, there are situations where you cannot implement RSA, you can hardly implement elliptic curve cryptography, but it's very easy to implement code-based encryption. So if what you need is encryption, code-based cryptography is competitive. If people are paying for it, so it's good.
What happens if post-quantum?
Yes. What?
Post-quantum. What will the quantum computation towards security?
I don't see the real opportunity for post-quantum cryptography as related to this fancy name, post-quantum. They are actually efficient. Some applications are efficient, others are not, but there are some applications that are very efficiently when conventional crypto systems cannot be applied. I'm personally a bit skeptical when, perhaps if large quantum computers can be built at all. However, even if they can, it's much more difficult. I mean, it's much less likely that they can solve NP-complete problems. If they could, then certain principles of physics would be violated. And Scott Aronson actually is now changing the point of view. Suppose that quantum computers are unable to solve NP-complete problems. Take this as a principle. Then you can prove that time machines do not exist. Actually, what you can prove is Stephen Hawking's conjecture of the chronology protection. So, nature will not show us an effect before its cause or so. And also you can prove that quantum mechanics is linear. So why that? Because if there is any nonlinearity, then you can solve an NP-complete problem. If you are starting from the assumption that quantum computers cannot solve NP-complete problems, then the whole of quantum mechanics has to be linear. It's an open problem since 1925 or 26. Why is quantum mechanics linear? You can prove that if you take as a principle that a quantum computer cannot solve an NP-complete problem. So even if a large quantum computer can be built, it's extremely unlikely that it could solve one of those hard problems. You can always devise some kind of crypto system based on some interactability assumption that not even a quantum computer could tackle. But I doubt any quantum computer will be able to.
You're asking if I want to go Shrek.
Shrek, no. Shrek.
Paulo will be hanging here around today, tomorrow, and probably some part-time next week also. So we can have many more minutes questions, I hope. That's the very final one.